Everyone, and welcome to this presentation of the Verified Carbon Standards latest approved methodology, VM0014, Interception and Destruction of Fugitive Methane from Coal Bed Methane Seeps. This methodology was recently approved in the middle of last month. I want to first thank all of you for your attendance here. We really appreciate your interest in this methodology, and we'll get introduction into this methodology from the lead author, as well as some insight from one of the assistants of the methodology. So we'll go ahead and get started. So first, just an introduction of who's on the webinar. Myself, Sam Hoffer. I'm a program officer with the Verified Carbon Standard Association. The lead author of the methodology, Mike Husinga, an associate engineer from WSP Environment and Energy, and also one of the assessors from Bureau Veritas, Dave Church, who is the Director of Climate Change Services. Just a bit of background on the agenda of this webinar. First, I'll give a look at the methodology approval process that this methodology was through. Next, we'll get an introduction of the methodology itself and some of the specifics of that. We'll also get some perspective from Dave from Bureau Veritas, and he'll give some insights on what validation and verification might look like for a project that's developed in this methodology. The last thing we'll do is a Q&A session. So for those of you on this webinar, you see on your control panel, there is a little icon for questions towards the bottom. And if you have any questions during this presentation, please feel free to type your questions in there, and towards the end of this presentation, we'll do our best to respond to all of those questions. So part one of the presentation, I'll just do a bit of background on the VCS methodology approval process. As many of you know, the process starts with a 30-day public comment period. Then it goes to assessments by an approved VCS validation verification body before being submitted to the VCS for final approval. So just to look at some of the timelines here, this methodology was originally submitted to the VCS on June 9th of 2010. The 30-day public comment period began on 15 June of last year and ended on 14 July of 2010. The first assessment was performed by DNV, and their first assessment report was finally issued. The final version of that report was issued on the 25th of May of this year. And the second assessment was performed by Bureau Veritas, and their final report was issued on May 24th, 2011. And once all of the methodology documentation and the final assessment reports were submitted to the VCS, final approval was granted on the 14th of June of 2011. And now what I'd like to do is pass it on to Mike of WSP, who is the lead author on this methodology. And he'll be giving us insights on, exactly what this methodology is set out to do, and some of the specifics of the methodology. So, Mike, I'll go ahead and pass it on to you now.
Thank you, Sam. And you can go next here. As Sam mentioned, my name is Mike. I work at WSP Environment and Energy. We were initially retained by the Southern Ute Alternative Energy Fund and the Southern Ute Indian Tribe to assist them with developing this project, to take it through validation verification, but also to get a methodology in place that would work for them. And the main kind of an objective of this methodology is to allow for projects that reduce methane emissions, fugitive methane emissions, essentially that result from the production of natural gas from coal bed methane production basins. And specifically in this case, in this project case, we're looking at the San Juan Basin. Any CBM basin would be applicable if certain conditions essentially were present that get these types of fugitive methane emissions. We'll describe more of those in a bit here. But suffice to say that the Southern Ute Indian Tribe operates coal bed methane natural gas production wells on their tribal lands, and they've known CBM seeps for quite some time, and they decided to kind of let's do something about this and see if we can try to prevent some of these emissions from occurring. So types of projects that are applicable under this methodology would be any project that is capturing and preventing the release of these types of CBM emissions at coal bed methane outcrop, essentially where the coal seam is exposed at the ground level and methane is being released from the ground level as it travels up these seams. The types of equipment that we could use are either vertical wells or horizontal wells, ground surface. A vertical well would be drilled, into the coal seam and try to capture methane as it's being traveling up the seam, and a horizontal well is trying to capture gas at the surface level before it gets emitted to the atmosphere. And applicable destruction systems are the usual suspects. You can clear, destroy it, heat of power generation, clean it up, and inject it into a pipeline. The main difference here between the coal mine methane methodology is there's no ventilation air methane, there's no VAM, thermal oxidation technologies for low methane concentration. Or it's not envisioned as being part of the methodology. Things that are absolutely not applicable under this methodology would be any type of active abandoned coal mining activities, pre-mine drainage, where they remove methane from a clean before mine. That is not applicable. Basically, anything involving coal mining is not applicable here. Active conventional CBM production wells are also excluded, although they essentially can be present near the project boundary, near the project location, in order for the conditions to occur, we think. So while you can't use a conventional CBM well, they would likely be very close to the project is located. And by what I mean by conventional well here is a gas well that pumps water out of a coal seam in order to reduce pressure in the seam and liberate gas that is trapped in the coal seam and trapped by the water. And this is what conventional CBM production does in order to free pull it out and produce it. And so that project activity is excluded from the messaging. Next slide, please. And so just a couple of schematics here, just in case no one's kind of really familiar with this. This first picture is kind of describing what I just mentioned here. The conventional well, water is pumped up from the seam and removed, and this liberates gas that's in the seam near the bottom here, and they can capture the gas as being liberated from the seam. And next, please. And in certain coal bed basins, there may be other geological conditions that are present which kind of result in fugitive emissions. And this is kind of the general project schematic layout. What we kind of think is going on while these emissions are occurring. On the fray, you can see a conventional producing CBM well is drilled deep into a coal seam, and there's a water level here, ground water level, and it's pumped out and removed, and sometimes this could result in fugitive emissions that travel then up the seam. So in this case, we have a coal basin where the coal seam is sloping towards the ground. And we think conditions create more fugitive emissions. The essential gas is it's hard to be captured by the well, and they travel up the seam in the fracture lines of the coal, and they're emitted at the ground surface level. So we envision that interceptor wells, basically fugitive methane interceptor wells, can be drilled into the coal seam at an intermediate location between the surface seeps and the active CBM production wells capture the gas as it's moving the seam before it hits the ground surface level and it's released. So that's the general idea here. Next, please. And this schematic is just kind of generally showing our project boundary. Again, on the far right, if we're kind of thinking that the same schematic as before, on the far right we have a conventional CBM well or well field. On the far left is the coal outcropping at the ground level, and fugitive methane emissions are being released. And then in between here is kind of our project activity. So a number of gas interception wells that would be located near the coal phase outcropping. Ultimately, your engineering study is going to need to determine where these are placed at optimal locations to capture most gas as it's traveling up the seam. So they capture and collect methane and deliver to some sort of a collection system. And gas could either be flared or used to generate heat power, or delivered to treatment and compression equipment for ultimate pipeline injection and use by end users. So the project boundary contains these types of equipment, and the emission sources are kind of showing up here. We're reducing fugitive methane emissions, and then by burning the gas, we release CO2 and CH4 and the flares, that kind of stuff. Next, please. So a couple of notes here on baseline and additionality for these types of projects. In the baseline scenario, as I described, fugitive methane emissions are traveling up these coal seams and they're being emitted at the ground surface level. We wanted to kind of include, because the boundaries are fuzzy and in many cases there's a lot of active CBM production wells in these areas, we wanted to kind of make it strict so that we could ensure only wells are used to capture fugitive gas and not wells that are being used to produce methane are applicable here. One of the things we kind of put in place is a requirement that there would be documented evidence that fugitive methane emissions are occurring at the ground level. There's a number of ways of doing that. I mentioned aerial differential LiDAR, where basically planes can fly over, scan ground surface, and map out areas where methane concentration or methane fluxes are higher. And there's also field measurement techniques where you can use various measurement devices to pick up methane flux rates at the ground surface level. And basically these are useful for project feasibility, but they're also kind of a project requirement here that there are documented evidence that methane is occurring, methane emissions are occurring at the ground surface level, so that it kind of prevents you from just kind of drilling into the seam and pulling more gas up, and you would otherwise be able to. So in the baseline, fugitive methane emissions are occurring, and there's also in the baseline there's avoided CO2 emissions from energy that is produced by the project. So if we displace heat or power generation or pipeline gas, that we're avoiding emissions from conventional production. Determining the baseline is outlined in the methodology. There's a prescribed approach to determine the feasible options for capturing gas, as I mentioned, the different well types that one could use, and then of course the different means of destroying gas all kind of show up in the definition of how one goes through and defines the baseline for the project. And then, let's see here. Actually, before I mention that, I wanted to explain this thing on the right here. Basically, in the baseline, there are there's fugitive methane emissions occurring at a coal seam outcropping. The project is only going to be able to capture so much of that gas. It can't possibly grab all of it. And so we consider the baseline emissions from the project perspective to only be the portion that is captured by the project. That fugitive emissions that continue to be emitting from the ground, or they evade capture by our systems, are essentially outside of the project boundary as we define it. And so it's really just a relative change in emission that we're kind of looking at. And we can go to the next slide. In the project scenario, there are, as I mentioned, destruction devices and hopefully energy reduction equipment on site to destroy the captured methane and we inventory the CO2 produced, or methane in some cases if it's a flare, and inventory these emissions from all the project equipment, and kind of the relative difference, like I said, is what we end up reducing. In the additionality assessment for the projects, we refer to the CIND tool, the CDM tool, for baseline and additionality assessment. As I mentioned, the baseline is kind of a prescribed approach for the first two steps of the tool. So you follow the approach outlined in VM0014. And then in terms of additionality, you basically just refer then to CDM's combined tool for baseline additionality and follow those steps. And you look at the usual IRR or common practice assessment. I think we can go next here. So just in terms of quantification, it's methodology, as you may have been able to gather if you're familiar with the ACM 0008 for active coal mine methane capture and use projects. It follows the same basic approach as this methodology. As I mentioned, the baseline emissions are kind of what we're capturing and what we're collecting in these collection systems. And the project emissions then are emissions that are resulting from the destruction of methane. So in many ways, it's very similar to the coal mine methane methodology. A couple of things have been changed. We've updated carbon oxidation efficiencies to 100%, and some of these methodologies that were developed before 2006 used efficiencies below 100%. IPCC updated some of these things in the latest guidance documents, and so this has been changed. It kind of simplifies the methodology in some ways. And we've also added and kind of clarified, I guess, language around the option of using pipeline injection as a means for methane destruction and utilization. So I guess the takeaway here is it's very similar to the coal mine methane methodology. If you're familiar with that, you definitely understand this one. And a couple of slight modifications to that. And then in terms of process, it's baseline emissions, as I mentioned, are emissions from methane destruction in the baseline if they were already occurring. If for some reason you expanded an existing project that wasn't a VCS project, then there would be methane emissions destruction in the baseline. And then the second term, methane reduction. So what we're reducing by this current project, and that's basically what we're capturing and destroying. And BE use is emissions displaced from energy production. And project emissions are methane destroyed by energy generation, or methane destruction. I'm blanking on that first term, I'm sorry. And the third term is uncombusted methane, which could result from flares. Anyway, the difference is the methane emission reductions of the project. I think that covers everything for me. I may have skipped a couple things that are pertinent, but feel free to ask questions here at the end. What do I have on a slide left? Oh, I do have slides left. Sorry. Okay, in terms of monitoring the project activities, follows the usual procedure. Developers would propose their plan during a project description and carry out regular monitoring. The main things to note here, I guess, are that we want to measure methane flow rates at the collection system, ideally at a central point after all these individual wells are combined and fed into the destruction equipment. It's easiest to just measure it there at a common point. And so we want to capture flow rates, adjust them for temperature and pressure, and we want to monitor the methane concentration of the gas and non-methane hydrocarbon content as well, because some of those, if it gets above 1%, we want to quantify emissions from destruction of non-methane hydrocarbons. And of course, we want to collect utility records and invoices for energy consumed by the project and energy sold by the project that goes into the grid or into the natural gas pipelines. And there are a number of factors determined ex ante before the project starts for fuel consumption, electricity use, that kind of thing. So I guess the main thing is to make sure you have a competent team of people who will be able to collect regular data for the gas chromatographs that are being used to meter these gas streams, and making sure they're calibrating flow meters, that kind of stuff on a regular basis. And all that data is maintained and kept secure and being used for the project activities. Next. Okay, that was it for me. All right, sorry.
All right, thanks very much, Mike. We really appreciate it. I think that gives everyone a very good understanding of exactly how the methodology works. What we'd like to move on to now is we'd like to pass it on to Dave Church from Bureau Veritas, who was one of the assessors of this methodology. And he's going to give us some insights on, sort of a bit about the assessment process, but also what validation and verification might look like under a project that was developed under this methodology. So, Dave, I'll go ahead and pass it on to you now. Dave, I don't know if you have yourself still on mute, but we're having trouble hearing you right now.
Okay, can you hear me now?
Okay, we've got you now.
Okay, I'm sorry. Thanks, Sam.
Okay.
Yeah. Okay, finding the mute off button is easier than finding the mute on button. Appreciate the opportunity to just provide a little bit of our point of view on the type of project and what the validation and verification might look like with that. Everything about validation revolves around what's in the PDD. And the process begins with a really complete, thorough examination of everything that's in the PDD. We like to say every word and every number in the PDD is important. And so we start there. And following that review of the PDD, we would do a site visit to observe exactly what's going on with the project, interview participants, and spend quite a bit of time just making sure we understand exactly what's going on. The focus for that, and as Mike was saying, one of the really important parts is making sure we understand the applicability for a project like this, because it is very similar to some other CDM methodologies. And so we want to ensure that we understand completely how the applicability has been determined and that it is it's not overlapping with some other process, or everything that's part of the project is exactly what the methodology requires. Another very important part, the boundaries, making sure we understand the scope, and that's really looking at how the project was established. It's really coming to an understanding of precisely how the project was engineered, what's included, what's excluded, making sure we understand how the gas is being recovered and exactly what's being done with it. Another part of this is making sure that we understand the baseline scenario. And this is probably one of the more complicated parts of the methodology, because you're recovering fugitive emissions, and so the measurement of that becomes extremely important. That is a place where we would probably spend most of our time, is looking at understanding the baseline scenario to ensure that what's being claimed as baseline is accurate, is complete, and as possible, so that we're sure that the starting point is exactly what it's supposed to be. Then, again, the methodology borrows heavily from the VCM0014 CDM methodology, and so it's pretty well established what the formulas and the equations are for this. But again, it's a matter of checking to be sure that what was implemented is exactly what's in the PDD. And in essence, the validation is a validation of the PDD. So we're just ensuring that it accurately describes exactly what's going on with these wells, how the recovery is taking place, how the gas is being measured, and how it compares to the baseline. When we talk about data requirements, there's an enormous amount of data that's collected in this process, as Mike was describing. There's ongoing measurement. There's a lot of calibration involved. So we're extremely interested in the accuracy and completeness of the data to support the conclusions and the assertions that are made about the emissions reductions. The verification of the data from this type of a project involves really going back through the records, and data verification is simply understanding two things. One is the data management process complete? Is it effective? Does it clearly identify all sources and measure correctly? And then two, is the data itself correct? So that's a two-step process in verification of the data. So the entire validation verification process for this methodology, very data intensive, but key again, understanding primarily the applicability and the baseline scenario, which we see as probably the fundamental parts of this. So I'll pass back over to Sam, and if there's any other questions later, I'd be happy to try to respond.
All right, great. Thanks very much, Dave. We really appreciate that. What we'd like to do now is move on to our Q&A session. If you haven't had a chance yet, please go ahead and type in any questions that you might have. So the first question that I have here is for you, Mike. And I was just hoping you could give us a bit of background of exactly, you know, where Southern Ute Indian Tribe came up with the idea for this methodology, and sort of what their intent was, you know, to create this methodology. You had mentioned a bit before, you know, they were concerned about this, these fugitive methane emissions, but maybe you could just give us a bit more background on exactly how this idea came to be.
Yeah, sure. I don't want to, say too much about their commercial motives for these projects, because I'm sure they wouldn't want me mentioning all those details. But basically, as I understand it, they have for at least 10 years been kind of well aware that these emissions are occurring. They are an active CBM gas producer, and they own and operate wells that are on their tribal lands, and they they explore and do various things looking for other project types in the area. And I think they kind of just became aware of the emission source at one point in time, and they kind of kept an eye on it and tried to monitor it. Back in the mid-2000s, let's say 2005 and 2006, they commissioned an environmental firm to do some field studies and try to get a better handle on basically the amounts of gas that were being emitted and from what areas. I mean, you can imagine it's occurring over a very large area, and so they wanted to try to map out where the highest concentrations of methane are occurring. And I think basically just through this process of doing some of these field monitoring measurements and doing some of the aerial LiDAR stuff, they kind of started realizing there's a real potential here. There's quite a bit of gas being emitted, and there's a real potential to recover it and to produce a viable project that makes money. It increases the efficiency essentially of the down dip coal bed methane production operations. If you kind of look at it that way, you've got a resource and you're extracting gas and trying to sell it. Anything that's lost is obviously an inefficiency and a waste, and it's resulting in very carbon intensive emissions, I guess. And they're well aware of that. So I think their motives are several-fold. They're environmental stewards. They consider themselves to be environmental stewards, but they're also resource in the business of resource extraction, and so they wanted to leverage their skills in that area, I guess, to produce a viable GHG reduction project.
Okay, great, thanks.
Mm-hmm.
Mike, we've got another one here for you. It's a bit of a long question, so bear with us. So the question is, it was mentioned that the baseline emissions include CO2 emissions from avoided energy production. And the asker of the question says, theoretically, these could be offset by emissions of CO2 from the combustion of captured methane. And so he's wondering, is the intent of the methodology to also give credit for reductions in CO2 emissions for energy produced from CBM, where the CBM may be a less carbon-intensive fuel relative to the baseline fuel?
I think the answer is yes. And so, the intent is to basically just kind of expand the project boundary a little bit, recognizing that a lot of this gas is being sold as either pipeline quality natural gas or power going to the grid. We just essentially look at what are the emissions associated with producing power, the equivalent amount of power that we're putting onto the grid, or the equivalent amount of natural gas from other conventional sources that are being displaced. So yes, I think the answer is yes, that if you burn natural gas and if you burn CBM that has been, fugitive CBM that's captured, the emissions kind of net out to be the same. In the grid power case, then the answer is, maybe. It kind of just depends how carbon intensive the grid subregion you're on, or country mix that you have to deal with. So yeah, you could end up displacing more or generating more emissions than what is on the grid already, depending on that. Hopefully that answers the question.
Yeah, absolutely. Thanks. So we've got one more for you here, Mike, if you don't mind. If you could just give us a sense of the volume of emissions that would be captured by a project that was developed on this methodology, and also sort of give us a sense of how this volume compares to the volume that would be captured under a traditional CBM well.
Well, I can't provide much indication on the first part of the question. I would say that volumes are going to be comparable to types of volumes you're talking about for a coal mine methane project, and it's just really going to be site dependent. A lot of coal methane basins wouldn't even have fugitive emissions occurring. Some of them may be very intense, and frankly, I don't think we know the extent to which they occur. I think a number of CBM operators have been very reluctant to even admit there are emissions resulting from this stuff, because of the regulatory consequences they might face later. So I think we don't understand the full extent of the emissions that are occurring at other basins outside of the San Juan Basin where this project is located. And so I don't know how large projects could get or how small they can get. It certainly depends on a number of geological factors that would dictate how gas moves up the seam and is emitted to the surface, if it's dispersed over larger areas or small areas. So it's really just going to be very site dependent. And in terms of how that volume relates to the volume of the coal bed methane being produced at the site, I would say it's going to be very, very small. But it's also kind of, it's also very difficult to tell. In this case, in the San Juan Basin, there's tens of thousands of conventional gas wells that are drilled into the seam and pulling gas up. And we just really don't know, when we have an interception and use project like this and it's capturing gas at a certain location in the seam, we don't know how many of the down dip wells are causing those fugitive emissions that we're able to collect. It could be from a couple wells, it could be from 10 or more. We just have kind of no idea. So it's kind of difficult to relate that captured volume to the production volume. But it's a drop in the bucket in terms of what's being produced from the seam.
Okay, great. Thanks, Mike. We'd like to pass it on to Dave. We've got one question for you. If you could just sort of give us an insight into what you think are going to be the most important parameters from this methodology when validation verification bodies are actually assessing these projects out in the field.
I think, again, the best way to answer that is, probably the most fundamental piece of this to ensure that there's actually emission reductions taking place is the baseline emissions scenario, and how that's determined. That's absolutely fundamental to this process, because measuring fugitive emissions is very, very difficult, and ensuring that that's correct is probably the most fundamental piece of this.